This is problem number 14 from chapter 13 on page 502. To what temperature would the spacer of problem 10 have to be heated so that it would slide over the shaft with a clearance of 0.02 of an inch? The ambient temperature is 75 degrees. Now, when we solved this problem, we had this data from that problem. I chose an FN5, and so the limits of size on I called it a sleeve, but they're calling it a spacer. That's this piece, and there's the shaft. So the question is, we want to put these two together. We want to heat this up enough so we're guaranteed that we have 0.02 of an inch clearance between the hole and the shaft. So how high of a temperature do we need to go to? What do we need to do here? Well, the key to that is to realize that as you heat up the member, it's going to expand. And if you go to page 496, you'll see equation 13.1 looks like this. It says that the amount of deformation, the linear increase in size when you heat something is equal to the coefficient of thermal expansion, so linear coefficient of thermal expansion, times the original dimension, the length, multiplied by the change in temperature. I'm going to use a capital T because I'm used to that. To me, a lowercase t goes with time, but it doesn't matter. Your book uses a lowercase t, as long as we understand what we're talking about here. Now, we were told that the material is SAE 1020. Now, notice we want the deformation here to guarantee that we have 0.02 of clearance. Now, the worst case scenario is where the hole is only 3¼ inches large and the shaft is the largest size. It's 3.2584 inches. So if we want 0.02 of clearance, we've got to go from here to this size plus 0.02. So we've got to go from 3.2522 all the way up to 3.25. Let's see, we need 0.02 more, so actually I'll have to roll that up, 604. Now, the difference between these two, going from this size to expand it thermally to this size, that's the delta we need here. That's how much change we need in the size of this hole. So we need the difference between those two numbers, okay? So let's see. The way I calculated that to make it easy is I realized, well, the difference between these two is 8.5 thousandths. So I know that delta is 0.0084 plus 0.02 of an inch. So see how that guarantees that this hole will be at least as large plus 0.02, so it'll be 0.02 oversized. So I know now that the delta is 0.0104. That's just the sum of those two. Okay, now the question though is not how much change does there need to be, but what's the final temperature? So let's rearrange this and solve for the change in temperature. The change in temperature would be delta over alpha L. And then, let's see, the final temperature would be T final minus T initial. That's just what the delta means. Or the capital delta is the expansion divided by alpha L. And so, let me get my eraser and get rid of some of this. We know what this number is. I think we can remember it. It's 10.4 thousandths. And so the final temperature of this part had better be its initial temperature, which is 75 degrees, plus however much we want it to stretch over alpha L. Okay, so now we can plug in all the information that was given. So this is 75 degrees Fahrenheit plus the necessary expansion. There's our 10.4 thousandths. Divided by alpha. What's alpha? That's the coefficient of thermal expansion. It's the linear coefficient of thermal expansion. So go to page 496, look at table 13.5, and you'll see that the coefficient of thermal expansion for SAE 1020 is 6.5 times 10 to the negative 6th. And that's inches per inch per degree. Let me just write that as 1 over degrees Fahrenheit. because the inch per inch cancels out, but really the inch per inch is inches of expansion per inch of size, okay? So per inch of diameter in this case. All right, so L, like I said, that's the length that's going to expand. In this case, it's the diameter that we want to make expand. And that diameter is just 3.25 inches. Okay, notice the inches go away. Since the degrees Fahrenheit is in the denominator of the denominator, then we'll have degrees Fahrenheit here, which will add nicely. So that all works out. And let's see, so the final temperature, now when I plug all this into my calculator, it comes out to 567.3 degrees Fahrenheit. So I'm going to have to heat it up pretty darn well. It's going to have to get pretty hot in order to slide on with 2 thousandths of clearance. Now, another interesting thing to note here is that 2 thousandths of clearance is really not that much. There's going to be significant contact between this sleeve or whatever they call it, collar, I don't recall now. Anyway, there's going to be significant heat transfer between this hole and this shaft. And when that happens, that hole is going to shrink. And so you have to be careful when you're putting two pieces together like this. One thing that can happen is that this can shrink so quickly you can't slide it into place where it belongs, because you usually are trying to position it axially on the shaft. The other thing that can happen is that this part, if you get a huge difference in temperature between these two and there's really good heat conduction, you can get this inner part cooling too quickly and generate high thermal stresses within the material because of a large temperature difference along a small region. You can cause cracking and things. So anyway, the goal, or our answer to the question, is that we need to raise the temperature. Of course, you wouldn't raise it by 567.3, you'd raise it by 600 degrees or something, you know, to make sure you got there. But that's what the calculations tell us for that problem. And so really this was problem 14, which was a continuation of problem 10.